So now we're going to talk about the weighted mean or weighted average. So that's where you've got some numbers, but they don't all count equally as one another. Some of them are weighted more heavily than others. Some count for more than others do. Like maybe in a class where the final exam counts as much as 2 regular tests, or where your final grade depends on how you did in homework and tests and a project, but they don't all count the same as one another. Homework counts for 15% of your grade, the project counts for 15%, and tests count for 70%. So that would be an example of a weighted mean. Those percents are the weights that are associated with the different things that make up that weighted mean. So with a weighted mean, each individual number, each value in the data has a weight associated with it. Sometimes those weights are given as percents. Sometimes they're given as just whole numbers like 1 or 2 or 3. But the way you calculate the weighted mean is you take each number times the weight that goes with it and add those together. And then instead of dividing by how many numbers there are, you divide by what the weights add up to. So here's an example. Let's say there's a class where homework counts 15% and tests count 85%. So those are the only 2 things that make up your grade, what you got on homework and what you got on tests. And let's say you got a 96 on homework and a 72 on tests. What'd you get for the course? What's your weighted mean? Well, right away, I can tell you that your overall average is going to be somewhere between 96 and 72. It's the weighted mean of those 2 scores, so it's going to be somewhere between them. But it's not going to be right exactly halfway between them because tests count for a lot more than homework. So that 72 is weighted a lot more heavily than the 96. So that weighted mean is going to be between those 2 numbers, but it's going to be a lot closer to 72 than to 96. So now that we know what we're dealing with here, let's actually calculate this. So how do we calculate it? This is that formula for the weighted mean. It means to take each weight times the number that goes with it, add those together, and then divide by what the weights add up to. So weight times number plus weight times number for however many numbers you have, divided by weight plus weight plus for however many of those you have. So the weights here are 15% for, oops, I got this backwards, didn't I? Homework counts for 15% and tests count for 85%. So it's 0.15 times the homework score plus 0.85 times the test score. And then we divide by just the weights added together, 0.15 plus 0.85. So if we put in the actual homework score of 96 and test score of 72, here's what it looks like. We got to take 0.15 times 96 plus 0.85 times 72, and then we got to divide that by 1, although dividing by 1 doesn't change anything. So when your weights add up to 1 or 100%, like they sometimes do, then you're not really dividing by anything. You're just dividing by 1. So when I put this into the calculator, 0.15 times 96 plus 0.85 times 72, and then if I divide by 1, that doesn't change anything. It's still 75.6. So I was right. It was between those 2 numbers, 96 and 72, but it was a lot closer to 72 than it was to 96. It was 75.6. Now let's talk about if you've got grouped data. You've got a grouped frequency distribution like we were talking about in section 2.1, where you got the classes with the class limits and the frequencies and all that good stuff. Here's how you would calculate the mean. This is the formula, but this is what it translates into. You've got to know the midpoint of each class. And then for each class, you multiply the frequency times the midpoint. And you're going to want to write that in a new column. Then add these together. That is, find the sum of frequency times midpoint. And then divide by the total frequency. So here's one example that's already worked out. This is based on one of the example frequency distributions that we saw in the last chapter. This part we've already seen. The limits, the midpoints, the frequency. This last column is new, but it comes from taking the frequency times the midpoint in each row. So 11 times 8 is 88, 12 times 23 is 276, and so on. Then when we add together the frequency times midpoint column, that adds up to 2,290. The frequencies themselves add up to 50. And maybe you remember this was based on a set of 50 numbers, 50 data values. So then to calculate the mean, we take that 2,290 divided by 50, and it comes out to be 45.8. So that represents like the average amount that people spend at this store. Some people spent between $1 and $15, some spent between $16 and $30, some spent between $106 and $120, but the average amount was $48 or $45.8. So now let's try one ourselves. And before we do that, the modal class is the class with the highest frequency. So that's real easy to find if you know what to look for. So in the example we were just looking at, the class with the highest frequency was the second class. Remember, the mode is the most common number if you just have a list of individual numbers. Well, the modal class is the most common class. It's the class that has the most values in it. So there were more numbers that were somewhere between 16 and 30 than there were in any of these other classes. That's why 16 to 30 is the modal class. So now let's try an example based on this frequency distribution. And if it looks familiar, it's because we came up with it in an example in the last chapter. But based on this frequency distribution, let's find the mean and the modal class the way we were just talking about. So first, what's the modal class? You can pause the video for a second if you want to think about it. But remember, it's the class with the highest frequency. So that would be, look at the frequencies, which one's highest? The 13, so which class does that go with? 11 to 15. That's the modal class. More people had to wait somewhere from 11 to 15 minutes than any of those other ranges of minutes. Now let's find the mean. This isn't quite as easy. It's going to take several steps. Now I'm going to get some of these columns out of the way because we don't need all of them. We just need the frequencies and the midpoints. So I'll leave those there, and I'll go ahead and leave the class limits. And I've put a new column on the end for frequency times midpoint. So in this first row, that's going to be 7 times 3, which is 21. And if you want to pause the video and see if you can fill in the rest of these, you can do that. Okay, now unpause it and you've either filled them in or you're waiting to see what I get. 9 times 8 is 72, 13 times 13 is 169, 7 times 18 is 126, 3 times 23 is 69, and 1 times 28 is 28. Do you remember what we do next? Yeah, we add this column up. So we add up these 6 numbers, and they add up to 485. We also need to know what the frequencies themselves add up to. They add up to 40. That was because we started out with 40 individual data values. And now what do we have to do to find the mean? Now what some people sometimes do, but it's wrong, is take this 485 and then divide by how many numbers we added together here, which is 6. And they say, okay, the average was about 80.8. That makes no sense, because the average waiting time couldn't be 80.8 minutes if none of the individual waiting times were any longer than 30 minutes. So we're not dividing by 6, the number of classes. We're dividing by 40, the number of individual data values in those classes. The idea here is that we had 7 data values that were somewhere between 1 and 5. So those 7 numbers that were all somewhere between 1 and 5 should add up to around 21. Then we had 9 numbers that were somewhere between 6 and 10, and so they should add up to somewhere around 72, and so on. So all 40 of those numbers should add up to, our best guess would be 485, and then we divide by 40 to get 12.125, and then to give that to 1 decimal place after the decimal point, we'd round that to just 12.1. So the mean here is 12.1 minutes. And that does make sense. One last thing to mention, I talked a little about distribution shapes when we were looking at histograms and that sort of thing. Let me say something a little bit more now that we have started doing some calculations. When you have a bunch of numbers, a bunch of data values, sometimes we say that they are positively skewed or right skewed or skewed to the right if there are lots of low scores, lots of scores that are below the mean, that are balanced out by 1 or 2 or just a few very high scores. The American Twiddle Company salary was an example. There were a couple people who were making big bucks, millions of dollars, and then most of the people were making a lot less than that. So most of the scores were below the mean, but you had a couple that were way above it. And so that set of numbers was positively skewed. It was like those two, the president and the vice president, they were making so much money, were skewing the average up or positively or to the right compared to where it would be without them. And then negatively skewed or skewed to the left is when there are lots and lots of high numbers that are above the mean, and then 1 or 2 or just a few that are way, way below the mean. And we saw an example of that in Class B, where most of the scores were in the 80s or 90s, but there was that one loser who got a 35. So that one score of 35 that was way below the mean kind of pulled the mean down and skewed things in the negative or left or lower direction. And then if it's not skewed either way, it's symmetrical. And that means the mean and the median are approximately the same as one another, and there are about the same number of values above the mean as there are below the mean. Okay, so I'm all done with everything I really needed to say in section 3.1 about measures of central tendency. But I will come back with one sort of extra bonus video for various technological ways of doing this on a calculator or a calculator app or an Excel spreadsheet or something like that. So watch that if you want to see some handy technology ways of doing things.